If you look at the stencils used to print modern microchips, the shapes look bizarrely mangled and warped. Microchips are built using photolithography, a manufacturing process where ultraviolet light shines through a glass stencil called a photomask onto a sensitive chemical coating. This projected pattern lays down the blueprints for billions of microscopic transistors on a single silicon wafer. When engineers try to print features smaller than the wavelength of light being used, diffraction takes over. Light waves spread out, bend around sharp edges, and blur. Perfect rectangular lines on a mask end up printing onto silicon as rounded, useless blobs. Instead of fighting physics, chipmakers use a technique called optical proximity correction. They feed the desired chip design into supercomputers that calculate exactly how light will warp, then deliberately deform the shapes on the mask in the opposite direction. If a transistor needs a sharp square corner, the photomask gets tiny ear-like extensions called serifs at its edges. Where lines run too close together, edges are thinned out. The mask design looks completely distorted, but it counteracts diffraction perfectly. Calculating these optical corrections requires massive computational power. Computing the modified pattern for a single modern microchip mask set can take thousands of server hours, running complex optical wave algorithms to precisely adjust billions of individual polygon edges. When ultraviolet light passes through this intentionally scrambled stencil, the wave interference naturally cancels out the distortions. The light lands on the silicon wafer with razor-sharp edges, creating clean rectangular wires that are only a few nanometers wide. By making the stencil look wrong, engineers get the light to print the chip exactly right. For more space and science, please subscribe and hit the like button.